Hi, my name's Kevin, and I will be your moderator for this afternoon. Thank you for joining us at MIPI DevCon 2021. Today's session will be MIPI D-PHY and MIPI CSI-2 for IoT, AI edge devices. AI at the edge is growing tremendously, so this session should be really exciting. Our speaker is Ashraf Takla, who is the president and CEO of Mixel, which is the leading provider of mixed signal and mobile IPs. Before we get started, I just want to let you know that the presentation will be available at mipi.org, and the link will be in the chat area on the right. With that said, we will also have time for a short Q&A after the presentation, so submit your questions in the chat area. I just want to please welcome Ashraf.
Hi, my name is Ashraf Takla, Mixel founder and CEO. Thanks for joining us here today. Our presentation is about using MIPI CSI-2 and D-PHY for AI applications in IoT edge devices. We will start with a brief overview of the benefits of edge computing. Next, we will look at the perceived Ergo and the system and device block diagrams. We will then cover the problem that Perceive is addressing with this solution and their target applications. Then we will cover why Perceive decided to use MIPI interfaces and why they selected an FDSOI process for their design. We will wrap up with an overview of Mixel MIPI IPs integrated into Perceive's chip and the silicon results. Let us review the benefits of processing at the edge. In most AI applications, quick response is essential. The ability to make decisions in real time with very low latency is mandatory. Edge computing plays a key role in meeting those demanding requirements and the high expectations of today's users. When you process data at the edge, you end up saving system power because less bandwidth is utilized. You also minimize false notification, which also improves battery life. From security and privacy perspective, edge processing reduces the chance for breach while the raw data is in transit to be processed remotely. Of course, the local edge device needs to be well protected and secured. In some locations, connecting to the cloud through broadband or cellular network may not be possible, so local computing is mandatory. When the connection is available, cost might be a hurdle that can be addressed by deploying edge processing. Now, let us turn our focus to the perceived Ergo. In edge devices supporting AI, you need a processor that is capable of machine learning. Perceive has done just that with the Ergo inference processor, which is designed for IoT and edge devices. It has 20 to 100 times the power efficiency of similar devices in the market and can deliver 4 sustained GPU equivalent terafloating point operations per second at 55 TOPS per watt. This horsepower can process large neural network using 20 milliwatt and support a variety of advanced neural networks, all at the edge. In this slide, we show how the Ergo can be integrated into a system for a typical AI application. The processor takes data from various sensors. On the left-hand side, you can see audio inputs via I2S, video input through MIPI CSI and CPI, and other information using I2C and I3C. In the middle of the slide, you see the processor with the NOR flash, which can be used for fast boot up. On the right-hand side sits the SoC, which receives both the perceptions and the raw audio and video data, which are used in tunneling applications. Let us now go over the Ergo block diagram. On the top left-hand corner, you see Ergo's built-in imaging interface section. This includes 2 MIPI and 2 CPI inputs and 1 MIPI output. It can support 2 simultaneous image processing pipelines, one high-performance 4K using 2 instances of the MIPI 4-lane D-PHY, and one standard high-definition using 1 instance. Moving down the bottom left-hand corner, you see Ergo's audio interface, which supports both mic inputs and a speaker output. Next, you see the CPU system in the bottom center. Its main function is chip management, data flow, communication with the processor. Some processing of audio is done by CPU subsystem, such as temporal to spectral conversion. The DSP engine does pre- and post-processing such as FFT. You can also see the Ergo's image processing unit in the top center, which processes raw images from the camera to make them more readily usable by the neural network fabric. It does functions like scaling, cropping, and color space conversion. The chip can perform inferences on images and video, and it can also offer the ability to tunnel video out through the MIPI transmitter. Tunneling is useful in many applications, such as security, where an alert can be accompanied by the corresponding audio and video. The Ergo then uses both audio and video or other sensor inputs to produce high-quality inferences. For example, motion detection, accompanied by the sound of breaking glass, might trigger a more trustworthy response in a security application. Let us now go to the brain of the Ergo. This is the neural network fabric you see in the top right-hand corner. The Ergo chip supports several neural network clusters, which allow it to simultaneously run multiple neural networks and support multiple input data types. For example, processing audio and video at the same time. The neural network clusters and their SRAM occupy over 2/3 of the area of the chip. This is where segmentation, identification, inferences, and other functions take place. Ergo is built to protect privacy and security without compromising speed, using an on-chip hardware accelerated decryption for the embedded software and neural assets. Perceive is targeting specific problems that edge devices are trying to solve. There are 2 main types of sensing, visual or audio. Each of these can be used to detect objects within the environment and recognize the user. Video object detection is used for home or enterprise security to detect interesting motion and ignore false alerts. Audio detection can detect critical sounds around the device to improve safety and contextual awareness. Face recognition can be used as a standalone biometric or part of a multi-factor authentication to unlock the device or objects. Speech recognition is used for wake-up words, device-specific commands, and natural language interfaces for smartphones, home appliances, and smart toys. Next, we will overview the different types of applications that the perceived device targets in some specific use cases. All the different applications use the same Ergo capabilities or a subset of them, so there is a lot of similarities. The way each one uses those capabilities is what differentiates each use case. Let's take a look at the smart home application, at a smart home application such as security cameras and doorbells. When using this processor for this kind of application, the system detects relevant motion and ignores false alerts, recognizes faces, voices, and people, detect relevant objects such as animals, packages, vehicles. It also uses voice or local command, detect important sounds such as alarm, alarms, people, glass breaking, etc. It can even describe the user, to the user people, vehicles, or the actions in the scene. For wearables, you can also detect important sounds around the user and use local voice commands and advanced wake-up words to simplify user interface. You can also recognize faces, voices, emotions, detect relevant objects around the user, and integrate data across multiple sensors. Next, let's take a brief look at how portable computing can use the Ergo capabilities. In addition to all the capabilities you already mentioned, the system can track eye location and interpret the user's emotion and attention using the built camera and smartphone. You can also blur or replace video conference background and improve audio and video quality. Looking at video conferencing devices, the Ergo is used in ways like those for portable computing, but can also support gesture or voice for touchless control. It can also be used to provide gaze correction and audience analytics. Now let's turn our attention to why was MIPI used in Ergo. Well, MIPI was designed from the ground up to minimize power while supporting high bandwidth and strict EMI requirements. Many edge applications are battery operated, so this fits in perfectly. MIPI CSI-2 and D-PHY are both widely deployed for sensor application. The D-PHY is the first and most widely adopted MIPI-PHY in the market today. In this block diagram, we have a typical IoT device using MIPI CSI and PHY. You can see the D-PHY or C-PHY are used to support both camera and display applications. Why did Perceive choose an FDSOI process versus FinFET? Let's start by looking at the cross-section of a typical FDSOI transistor. Here, the channel is isolated for the bulk, which allows us to apply forward or reverse bias, resulting in the ability to control the transistor's threshold and leakage currents. Because of that and the inherently lower parasitics, FDSOI provides the right mix of features to achieve higher performance at lower power and lower cost without the need to move to the more costly FinFET processes. Compared to bulk silicon, FDSOI enables us to achieve higher performance and potential reduction in power and area because of the lower parasitic and back bias programmability. Body bias allows us to make trade-off between dynamic and leakage power to achieve lowest overall power consumption for a specific workload and operating conditions. For example, reverse body bias can be applied during standby mode to drastically reduce leakage current. FDSOI also enables performance and speed boost through forward body bias. It's no surprise that FDSOI is widely adopted in IoT devices. We conducted some analysis to quantify these benefits. In this evaluation, we applied forward bias to save area and reduce power. By doing so, we found that potential active area could be reduced by up to 55%, and the power could be reduced by up to 50% across PVT without any performance degradation. Let's now look at the Mixel MIPI PHYs integrated into the Ergo. We provided Perceive with MIPI receiver and transmit IPs, which were silicon proven in another FDSOI process before we ported them to 22FDX. On the receiver side, we delivered two different area-optimized receiver configurations of the CSI-2 D-PHY, a 2-lane and a 4-lane versions. They both support MIPI D-PHY 2.1, which is backward compatible with V1.2 and V1.1. Both configurations run up to 2.5 gigabit per second per lane and support a low power mode running up to 80 megabit per second per lane. For the TX side, we provided Perceive and area optimized 4-lane CSI-2 D-PHY. This IP also supports MIPI D-PHY version 2.1 and has a high-speed transmit mode running at 2.5 gigabit per second per lane. This transmitter is used to support the tunneling function. Here you see eye diagrams of the TX IP running at 1.5 gigabit per second per lane and 2.5 gigabit per second per lane. Perceive achieved first-time success with the Mixel IPs and is now in production. Here is a quick overview of the Mixel silicon-proven IPs in 2 different FDSOI nodes and foundries. You can see a mix of D-PHY, transmitter, receiver, and universal lane configurations, together with LVDS and D-PHY LVDS combo IPs. All those IPs are silicon proven with first-time silicon success. For those of you who are not as familiar with Mixel, we are an industry leader in MIPI interfaces and a contributing member of the MIPI Alliance since 2006. We have a long track record with MIPI, with our MIPI D-PHY first silicon proven in 2008, MIPI M-PHY first silicon proven in 2011, and MIPI C-PHY first silicon proven in 2016. We offer a complete integrated solution, including the PHY, controller, and FPGA platform. We believe we have the widest coverage of process nodes and foundries for the MIPI PHYs. We are silicon proven in 11 different nodes and 8 different foundries. Let us now conclude by summarizing the presentation. Edge computing provides many benefits, including the ability to make decisions in real time with very low latency. MIPI specifications were uniquely developed to support low power, high bandwidth applications for mobile and edge devices. FDSOI is well suited for high performance application at lower power and cost compared to FinFET technologies. That makes MIPI specifications and FDSOI technologies a great match for edge devices. Processors like Perceive Ergo enable AI processing at the edge to make IoT devices smarter, achieve lower latency, and improve battery life and security. Mixel worked closely with Perceive SoC designers to leverage the benefits of MIPI in silicon-proven FDSOI IPs, achieving the shortest path to first silicon success and high volume production. Many thanks to all of you for participating today.
We have time for maybe one quick question. So what I'd like to ask you is, with everything you shared about processing and all this activity going on at the edge, what future trends do you see happening in edge devices using MIPI specifications moving forward?
Thanks, Kevin. Like any other segment, the quest for higher performance at lower power and lower cost continues. The question is, what will that entail for edge devices? We have seen accelerated adoption of the C-PHY D-PHY combo. Adopters like that very much because it gives them the option to support both specifications. Recently, we see a move to some customer requiring C-PHY only solution. That said, for the foreseeable future, we see that the D-PHY will continue to be the most widely adopted specification. I think we are out of time. So I will hand it back to Kevin.
Okay. Well, that is all the time we have for now, but we thank you all for attending.